Hello everyone! We are going to finish up section 1 from chapter 12, which is about gases, and then we're going to start on chapter 13. I just want to go over the first gas law, which is Boyles Law. I don't think that the video will take us very long, so we're just going to go ahead and jump right in. We kind of left off here with gas pressure, and somebody who was really influential with calculating the pressure of gases, or just talking about pressure to begin with, is a guy named Torricelli. And Torricelli was the one who invented the barometer, which we still use today. We just kind of use a different version of it that's safer. Basically, barometers are instruments that are used to measure atmospheric air pressure. Now, Torricelli's barometer looked a little bit like this, and he ended up having a glass column in here, and he had a pool, kind of like a little, just like a bowl, but in his terms he would call it like a pool of mercury. Now, as you could probably figure out, it's not safe for us to use this mercury now, so that's exactly the reason why we don't use his version of the barometer. But what would happen, the atmospheric pressure will push on this mercury. So the mercury, if the atmosphere is pushing on that mercury, then that mercury can go up into this column. And then he figured out that however much mercury was in this column, that's how much atmospheric pressure there was for that day. So because of his barometer, we kind of started this trend with weather patterns and meteorology. So he was really huge and influential in kind of sparking this new idea about weather patterns and how much is the atmosphere really, how much atmospheric pressure is really being exerted today. So this barometer was big in that. So again, we just don't use it today because of the mercury. But there is another type of instrument that we can use to measure gas pressure, which is a little safer, and that's called a manometer. And a manometer will measure gas pressure using a closed container. So this is what you'll start off with. You have gas that's trapped in this part of the container, and then I have some levels of liquid that are in here, and this end is closed up here, so it's kind of like a nice closed system. And I can tell that when the gas is closed, that these levels here are going to be equal to one another. When I open this gas valve, so I'm opening this valve, so now it's open over here, gas is able to be released, and it'll start to flow through this through these columns. And I can tell that now I'm seeing a difference in the levels. Over here they were equal, and now they're different. So based on how much this liquid on this side will go up, this difference will determine how much pressure the gas can exert. So this is just another way that we can figure out how much pressure a gas will exert. Of course, the gas could exert so much pressure that it could make that level of liquid rise all the way to the top. And if that were to happen, we'd have to change the concentration of gas that we have that's trapped in here. So if that happens, we can ultimately fix that problem, so it's not too big of a deal. Okay, so just to talk about gas pressure, the SI unit of force is the Newton, and I just threw that in there because a Pascal is a type or a unit of pressure. And a Pascal is based on newtons, which has to do with force. So a Pascal is equal to a Newton per square meter. And I want you to think about, a few slides ago, we talked about that gas pressure, or pressure in general, is equal to the force of something per that area, per that surface area. So force is measured in newtons, and if I had area, it could be measured in square meters. So pressure then could be force over area, or a Newton per square meter, okay? Now, I don't care so much, I guess, about the newtons and then this Newton per meter squared right now. What I care about is that you know that we're going to use a unit of pressure, the Pascal. And another unit of pressure that we're going to use is an atmosphere. And 1 atmosphere is going to be equal to 760 millimeters of mercury, which think about this too, that Torricelli, his barometer was based on mercury, and that column was calibrated in millimeters. So for him, a unit of pressure that made sense to him was millimeters of mercury. So that's why we have millimeters of mercury as being a common type of pressure. Another type of pressure is kilopascals, where we just said it's the same thing as a pascal, only of course now we have kilopascals. So pascals, atmospheres, millimeters of mercury, and kilopascals. And just in case you forget, we have this fantastic little chart here, and this is just saying 1 atmosphere, which you are going to need this. So this column right here of this table is what I want you to be, you're actually going to need to start to memorize these. 1 atmosphere is equal to 101.3 kilopascals. Or 1 atmosphere is equal to 760 millimeters of mercury. Or 1 atmosphere is equal to 760 torr, which torr, oh my gosh, you would never guess, was a pressure derived by Torricelli. 1 atmosphere is also equal to 14.7 psi. Or we have 1 atmosphere is equal to 1.01 bar. There are just tons of units of pressure, and so the reason that we have these is because let's say that the barometer that you were using measures in millimeters of mercury, but I want to know how many atmospheres there are. I need to be able to convert in between those units. So this is going to be definitely helpful for if we ever need to convert units of pressure. Okay, so that's why that's going to be really important to know. Lastly, for this section, we have one more law of gases, and that's Dalton's law of partial pressures. And ultimately, what Dalton was saying was that the total pressure of a mixture of gases is equal to all of the types of gases that you have, or the partial pressures that each gas is contributing. So, partial pressure of a gas is going to depend on the number of moles, the size of the container, and the temperature. And it's independent of the type of the gas. So, I want to go to this. So Dalton's law of partial pressures is going to look something like this. My total pressure is equal to one of my partial pressures plus another partial pressure plus however many samples of gas that I have in there. So in this case, I had a mole of helium, and then I have a mole of nitrogen. So here's one partial pressure, here's the other partial pressure, and I know the total is just going to be the mole of helium and the mole of nitrogen. But then what would that look like if we actually had maybe a problem that dealt with partial pressures? Really, they're really, really easy. Okay, so let's try this one. I have find the total pressure, and I hope you can read that. That writing is pretty terrible. Find the total pressure for a mixture with the following partial pressures. You have 5 kilopascals, 4.56 kilopascals, 3.02 kilopascals, and 1.20 kilopascals. So I have 4 gases that are in this mixture. And let's say that my first partial pressure was 5. My second partial pressure was 4.56. My third was 3.02. And my fourth was 1.20. So these are all of my partial pressures, and I want to know the total pressure. Well, according to Dalton, I just add up all of my partial pressures to get the total, and that's all you have to do. So I'm going to take all 4 of those numbers, add them up, that'll give me my total pressure. And that should be 13.78 kilopascals. So that's my total pressure. All I did was add up those partial pressures to give me my total pressure. That's it. Pretty simple. So let's do one more. Okay, let's say that you have a mixture of oxygen, carbon dioxide and nitrogen. Your total pressure of this mixture is 0.97 atmospheres. What is the partial pressure of oxygen? If you know that the partial pressure of carbon dioxide is 0.70 atmospheres and the partial pressure of nitrogen is 0.12 atmospheres. So in this case, I know total and I know two partial pressures, but I need to know this last partial pressure. So if I were setting this up, and I hope that you have that slide with you, I know that my total pressure is equal to partial pressures, and I have three of them. And I guess instead of saying those three, we can actually just write what the compounds are, or what the elements are. We have oxygen, we have carbon dioxide, and we had nitrogen. So I knew from my problem that the total pressure was 0.97 atmospheres, so that was my total. They asked me to calculate the partial pressure of oxygen. So I want to know the pressure that oxygen is giving to this total. I know that carbon dioxide had a partial pressure of 0.70 atmospheres. And then I know that nitrogen was contributing 0.12 atmospheres. So all I have to do is solve for my partial pressure of oxygen. When you do that, you should get your partial pressure of oxygen to be 0.15 atmospheres. Okay, so doing these problems is not difficult by any means. You're either adding them all up, or you're going to add up what you have on one side, subtract from the total to get whatever your partial pressure is. So these should not be challenging or difficult or scary at all. Okay. Now, that takes care of our gas section in chapter 12. So now we're going to kind of move in to gas laws. And the first gas law that we'll talk about is Boyles Law. Now, Boyles Law states that the volume of a certain amount of gas that's held at a constant temperature will vary inversely with pressure. So what does that mean if it's varying inversely? What do you think that means? So if it's varying inversely, then when one increases, the other one would decrease. If one decreases, the other one would increase. So let's look at this one. I have a really big volume, and what would my pressure be like in that? If I have a large volume, the pressure would be pretty small. Let's say I compress this. Let's say I take this sample and I compress it. Now my volume is decreasing, but the number of collisions inside of that space is increasing, which is causing more pressure. So as my volume is decreasing, here my pressure is increasing. So here's that inverse relationship. Lastly, I'm going to decrease that volume even more. So then my pressure would increase even more. So if we graph these changes, we can get this graph to kind of look like this. So I just wanted to show you what the pressure volume graph would look like if we were to graph them. And Boyles' law, which you will be required to know, is this down here. P1 times V1. My initial pressure times my initial volume is equal to P2 V2. My final pressure times my final volume. So temperature and the amount of gas are always held constant in Boyles' law. So Boyles' law is only dealing with pressure and volume. So we're really only comparing pressure and volume in this. So I want to do a few examples using Boyles' law, which again is P1 V1 equals P2 V2. And I have, let's do this first one here. So example number 1 is that a bacterial culture produces 60 milliliters of methane gas at 700 millimeters of mercury. So I'm initially starting out with a volume of 60 milliliters and a pressure of 700 millimeters of mercury. I want to know what volume would be produced if that pressure increased to 760 millimeters of mercury. So since I'm comparing pressure and volume, that's Boyles law, because Boyles law compares pressure and volume, or deals with pressure and volume. So Boyles law is P1V1 equals P2V2. And I know initially my pressure, I have 700 millimeters of mercury, because I know millimeters of mercury is a unit of pressure. So I'm going to write in here 700 millimeters of mercury. And I need to times that by my initial volume, which was 60 milliliters. So times 60 milliliters. And that's going to be equal to what my sample will be at the end of this. So what volume would be produced at 760 millimeters of mercury? So that's my P2, that's the next pressure. It's going to be 760 millimeters of mercury. And then I'm trying to solve for my final volume here. So I'm going to take these two and multiply them. When I do that, you should get 42,000. What is that? Millimeters of mercury times liters, because we just multiplied those units. And then that's equal to 760 millimeters of mercury times my volume. I want volume by itself, so I'm going to divide both sides by 760. When I do that, my volume should be equal to 55. And now I need to figure out, oh, sorry guys, this is milliliters. I need to figure out what my units would be. Well, if I divide my millimeters of mercury by each other, those would cancel, so I'd just be left with milliliters. So we should get 55 milliliters here for our final volume. And let's think about this logically. If my pressure increased, and I know that pressure and volume are inversely related, then the volume should have decreased. And that's exactly what you saw. My pressure increased from 700 to 760. My volume decreased from 60 to 55. So we can think about those logically as well, just to make sure that you know that you're getting the right answer. Okay, so I'm going to stop here because we're at almost 18 minutes and I don't want to make it go anymore. So tomorrow, make sure that you kind of have an idea of what you want to take for your science class, because we're going to talk about that because it's recommendation day tomorrow. And I'm also going to give you practice with doing Boyles law, as well as maybe some pressure conversion calculations too. So I will see you tomorrow. Bye!